잠깐만요. 스크린 공유. 처음 시작하실 때 이렇게 눌러주시면은 어떤
잠시만요. 또 안 돼요?
아니요, 새 걸로.
Hello everyone.
마이크로. 그리고
Hi.
소리가 작을 텐데요. 한번 해보고 최대한
Alessandro.
네, 한번 안 나오. 충분하지 않죠. 네, 코드는 될 것 같아요.
So should we also try to connect iPads, or I think Alessandro said that we should have some device. So
Yeah.
너무 작죠?
Oh. So I think we may need to register our tablets as well.
You need two links. That might be the quickest way to do it. Yeah, just put Fernando's tablet and something like that.
Yeah, actually, I am not entirely sure. I think when you register, it sends you a link, and then you can directly click that link.
Yeah, but it looks
works
like
for me. I have my
personalized
iPad connected now.
I think I have now my.
이거 한번 테스트 한번 해.
그러니까 들려요? Hello, can you hear us?
Yeah,
Yes.
I can hear you.
Good, great.
알레산드로로 시작을 하면 될 것 같습니다. 네.
So perhaps the host can check that Pedro, Fernando, and Lorenz can share their screen and share their tablet and give them all the necessary authorizations.
Yeah, I don't have a tablet. If I need to write formulas, I'll use Mathematica. I will just share.
That's great. So Pedro will use his screen, whereas Lorenz and Fernando have other accounts.
Yeah, I have a tablet. Shall I try to share the screen to see what happens?
Try to share.
Yeah, let's see. So share content, screen, I guess.
Yeah,
all right.
See it.
Fantastic.
Yeah, wonderful.
So, sorry. Oh, great. Oh, I was taken out of sharing by someone, perhaps.
Were you? Okay.
Let's see if I can, sorry. So share content, screen broadcast, start broadcast, I guess. Okay, good. And now, sorry, but let me see that.
Yeah.
Okay,
it looks
good.
Fine. It looks
Perfect.
fine. Yeah.
Perfect.
Okay, great.
Okay, we are ready. So, Alessandro, yeah, you can first start whenever you are ready.
Okay, perfect. So, good morning or good evening, everybody. So I'm in the US, where it's the break of dawn. People in Korea, of course, it's pretty late in the evening, and in Europe, I guess it's lunchtime. So thank you very much for joining this panel discussion, which will be about exact approaches to computing non-planar observables in ADS-CFT. And I'm very happy to have here to be joined by three very distinguished experts on the topic. We have Fernando Alday from the University of Oxford, who worked in his career on many aspects of ADS-CFT, and including integrable models, but most recently he's been using a bootstrap approach to study non-planar observables by using conformal symmetries, analyticity, and other ideas that he will tell us about. And then we have Pedro Vieira from Perimeter Institute and ICTP in Sao Paulo, who is one of the main driving forces behind the correlation function of study in ADS-CFT by means of integrability, which also led to very spectacular advances for the computation of non-planar observables. And Lorenz Eberhardt, who is a postdoc here at IAS, who is an expert in two-dimensional conformal field theories and has been using them, among other things, to study non-planar observables in string theory, and in particular in ADS3 CFT2. So, welcome everybody. What I would do is that I would ask each of you to give a very brief introduction to some of the ideas that you think are most relevant from your point of view to the study of non-planar correlation functions. So first, everybody would give a short presentation, and then I would open up the discussion after everybody has given maybe their short presentation. And since Fernando has already the screen share active, I would suggest that maybe Fernando can just start. Why not? Please take it.
Okay, thank you very much. So thank you for this wonderful opportunity. It's a pleasure to be here. And yeah, I wasn't intended to be the first one, but I just shared my screen and then I left it there. So I will try to give this 5 minutes presentation, but then of course you can ask me later as many questions as we want and as you want. And I hope the discussion flows in a very informal way. And as Alessandro mentioned, my approach, so the approach I have been interested in over the last few years is a bootstrap approach to the problem of non-planarity. So the basic observable that one wants to study is a gravity, or more precisely a string theory amplitude on an anti-de Sitter spacetime, represented by this closed string worksheet. Now, ADS is like a box, so you cannot really define asymptotic states because you cannot go as far as you want. However, the holographic principle and ADS-CFT tell us what the definition of a string amplitude on ADS should be, and it should be given by correlators of local operators at the boundary of this ADS space. And if we have, for instance, a 4-point amplitude, which is a function of two Mandelstam variables, that maps to a 4-point function correlator of the conformal field theory living in the boundary. And the idea then, once we have mapped this amplitude to this correlator, is to try to use bootstrap ideas and symmetries, integrability, whatever we have at our disposal to compute this object over there. And the ADS-CFT duality, the ADS-CFT dictionary tell us that for the case of, let's say, n equals 4 super Yanni Mills, which is dual to strings on ADS 5 × 5, tell us that the genus or the loop expansion on the ADS side corresponds to a 1/n, or more precisely 1/n squared, which is 1 over the central charge, expansion in the conformal field theory. And in this case, we have two parameters, stringy corrections to supergravity that corresponds to alpha prime corrections, correspond to 1/λ corrections on the CFT theory side. So the game, in the usual case of n equals 4 super Yanni Mills, is then to try to compute these 4 correlators in a double expansion of 1/n and powers of lambda, as I have shown in this picture. So the correlator then will have a generic expansion where the leading order is the disconnected contribution or mean field theory or general electric fields, that is at n equals infinity. Then we have an expansion that starts with 1/n squared, the non-trivial part, This is what is usually called the supergravity result. And then the supergravity result is corrected by a tower of lambda corrections, lambda to the 3/2, etc., etc. And in addition to that, of course, in addition to disconnected and the tree-level result, we have all loop results plus ... with higher loops, etc. And the structure of, if you have a look at the tree-level, for instance, results, this structure follows from the structure of the string theory effective Lagrangian, which is something like R plus corrections to supergravity. So we have, for instance, alpha prime cube R to the 4, D4 R to the 4, with some coefficients here. And this structure mimics this result. But from the point of view of the conformal bootstrap, etc., it is better to look at an observable, like the 4-point correlation. And the state of the art in these double expansions is that when you have this expansion, things like exchanges and loops from these exchanges can be determined from analyticity and ADS unitarity, and things that people may call the analytic bootstrap or the analytic conformal bootstrap. While on the other hand, these contact terms, the overall coefficients in front of these contact terms, are not fixed by obvious crossing symmetries, etc. But it turns out that the first few contact terms can be determined by localization constraints. In addition, if you are looking in a 1/n expansion with fixed G-Yanni-Mills, which is a bit different of the planar expansion, then S-duality also leads to some constraints. And big questions in this program are, for instance, what about all other contact terms? So here we have that the first few can be determined from localization. I can tell you a bit more about it if you ask me later. But there is an infinite tower, and we don't know how to fix this infinite tower. And a dream, something that would be like a dream in this program, is to be able to compute this whole tower, and this would be the Virasoro-Shapiro amplitude in ADS. So it would be the anti-de Sitter equivalent of the Virasoro-Shapiro amplitude. And I think the most promising idea to start computing all these coefficients is by trying to combine the analytic with the numeric bootstrap at large n. And something that I also wanted to add is that one has a similar situation in theories involving M theory, for instance, the 6D 2,0 theory. But in that case, one has a single expansion in terms of inverse powers of the central charge. So the global picture is that we have three maximally supersymmetric theories, three-dimensional ABJN, which is dual to M theory on ADS 4 x S7, 4D n equals 4 super Yanni-Mills, dual to string theory on ADS 5 x S5, and the 6D 2,0 theory, which is dual to M theory on ADS 7 x S4. And for these two, we have localization constraints. This one is dual to a string theory, and these two are dual to an M theory. And basically, this is what I wanted to say, and these are some of the main questions in this program. Thank you.
Thank you very much. It was a wonderful introduction also to the problem sort of in a broad sense. So maybe I suggest if Pedro wants to go next, would that be fine?
Yes. So let me unshare, I guess. Stop. Yeah.
Please go ahead.
Okay, can you see my screen? And can you hear me?
Yeah.
Yes.
Yeah.
Okay, so, oops, sorry. Let me bold all my collaborators. Somehow I forgot a few. Okay, good. Okay, so yeah, so let me tell you a little bit about what's the status right now. What do we know about non-planar physics from an integrability point of view? It's not that I know much. I only wrote 3 papers with a bunch of collaborators. Some of them I see that they're in the audience, so they can correct me if I say anything wrong. And I'm learning a little bit more right now with my student. But it's also easy to tell you what the little I know, because not much is known about non-planar physics from integrability anyway, so it's fine. Now, integrability, of course, is about the specialness of the two-dimensional worldsheet. So n=4 super Young-Mills, which is what I have in mind throughout this presentation, is integrable because the dual string theory is integrable. And that just means that when excitations of this two-dimensional string meets, they scatter in a factorized way. Of course, this is a local concept. It's not a topological one. So if I have a worldsheet and there are some excitations that are meeting, 3 of them, say, they scatter in a factorized way. So they scatter in a way that doesn't matter the order of the scattering event. Because it's kind of a local concept, that it's a property, a special property of the worldsheet, of the material that the strings are made of, it should not be a topological property, and therefore we would expect integrability to hold for any topology, and therefore to any genus in the 1/n expansion. So this, I would say, should be our basic expectation. By the way, let me make a side remark that I just added now as I was listening to Fernando's presentation, that from this point of view, obviously, string theory likes long strings. And even though we can have any worldsheet we want, big worldsheets are much better because there's lots of space for things to scatter. And so it's always a challenge, and it can be sometimes be seen as a feature, sometimes as a bug, this thing that integrability likes big strings. So it means that we can study processes that really probe string theory, where I have strings that are extended objects and they open up and they become big and then they interact and so on. So that's good. We can study really string theory, not field theory. But sometimes it's bad, because one of the things we often want to take is field theory limits. Take the limits where the string tension is very big and the strings behave like particles and so on. And that's often a challenge in integrability. So now this basic idea that the worldsheet, the material is the same, and therefore everything should be integrable, was not thought of like this before. So if you think forget about the worldsheet and think from the point of view, say, of spin chain Hamiltonians, which will be the picture in the middle, you could be worried about integrability, because you start with some theory which is planar, and that leads to a local Hamiltonian on the spin chain of n=4 super Young-Mills, where you have a bunch of local interactions. And when you start adding non-planar interactions in the spin chain, it looks like you are adding long-range interactions between the various spins of the spin chain. And spins where you start with local interactions and then you start having these non-local interactions are never integrable. It's very hard to have integrability for these types of spin chains. And indeed, if you study those spin chains and compute their spectrum and so on with local interactions and non-local interactions, they will not be integrable. There will be no degeneracies, and you will not find the features that you will normally find for the spectrum of an integrable theory. Also, if you think from the point of view of a worldsheet, like you have a cylinder and you think of non-planar corrections as corrections to that cylinder, it also looks like something very funny, that you will be introducing wormholes in your field theory, right? So you have your cylinder, and now suddenly particles can at some point enter some wormhole and appear later. And from the point of view of the cylinder, it also looks like you are introducing new rules in the game, some very non-local effects. Again, that is because if we are forcing ourselves to think of non-planarity as corrections to a planar theory, we want to insist on having the Hamiltonian plus some non-local effects, or the cylinder plus some non-local wormholes. But the point of view that we now mostly try to follow is the one on the right, where you have some worldsheet, for example, a cylinder with a genus 1, so it's no longer a cylinder. I don't know what the name of this is, but okay, it's a cylinder with a hole. What you do is you cut the cylinder in the hole, in this case, in 4 hexagons. And these hexagons are patches of worldsheet that we know how to describe using integrability. And then we just need to glue them back together. The just is very tough, because you have to glue the hexagons together and sum over all the intermediate states. And so this is the general framework that we have right now. For an endpoint function of genus G, we have a bunch of hexagons. I wrote the number there on the slide. It's 2n + 4g - 4. We have a bunch of, you have to glue these hexagons. These are patches of surface. They are like triangulation of the surface. There are many sums you have to do over the intermediate states of a complete base of states when you glue. And there are also discrete sums that you can interpret as a discretization of the string moduli. And I can talk a little bit more about it. Okay, and in field theory, this comes about from summing over the various possible weak contractions. Of course, this has bad features and good features. It has bad because these are many sums. These are infinite sums because it's a sum over a complete state, a basis of states on the worldsheet. So it's an infinite sum. So that's bad. But it's good because these blocks, these hexagons that are 4 in this picture on the right, there are 4 colors there, right? So you see 4 patches of surface. They are known at finite coupling. So if you could do these sums, you will get the full result. It will be the result for a string theory amplitude at any finite coupling. It will be like what Fernando was saying. If you do it for a 4-point function, that would be Virasoro-Shapiro in ADS, for example. Now, of course, ideally, we would get rid of the bad stuff and keep only the good stuff. And so we could ask if we could do these sums. So this would be the big problem. Is there something more powerful? And the answer is, we were already in such a situation in the past for the spectrum. At some point in the spectrum, we knew we had some result, and then we had many sums that were interpreted as finite size corrections on these cylinders. And then eventually, right now, we don't even talk about those finite size corrections. We have this much more powerful quantum spectral curve that resums them all. Whether such thing exists for correlation functions, we don't know, although for correlators of big R charge, that seems to be the case. Okay, so a few slogans that I would say is that integrability for finite n is probably too good to be true. I mean, after all, we know at finite n we have gravity, fluid dynamics, chaos, and so on, literally, right? So there will probably not be integrability in the general sense for finite n, I would say. On the other hand, integrability for each order in 1/n expansion, which in the beginning the days of integrability was thought as not being there, I would say now I hope everyone believes it's there, and it's now a rather conservative statement. Of course, for some simplest quantities, if we can compute all the terms in the 1/n, we might be able to resum them. And of course, I'm being pessimistic, but in a sense, when I say that integrability for finite n probably is not there, and maybe we can find some positive surprises by combining integrability with methods that are more friendly to finite n. Localization would be the main one, but the bootstrap as well. And of course, I did not mention at all, I was talking I had in mind mostly strings, scattering, and with all their 1/n corrections, so the physics of strings plus the 1/n corrections. But in string theory, there is more than strings. There are D-branes and other extended objects. And I did not mention them, but I do recommend a beautiful review that Shota gave at Strings about those. And we could discuss a little bit more. This would be related not to single strings, which are local single trace operators in the theory, but to determinant-like operators and so on. And lots of progress has been made in this direction as well in N+4. Okay, so I think I'll stop here, and this will be my summary of more or less where we are.
Okay, thank you very much. And I think now it's Lorenz's turn to tell us something. And I suspect it will take us to the low-dimensional world.
Yeah. Okay. Yeah, actually, I was taking the title of the panel discussion to be slightly more general. So I'm just
which
talking
you are welcome
about. Yeah, so my expertise is in two-dimensional CFT, so in particular worldsheet theory. So I thought I'd just talk about what's the rough status and what are the problems of perturbative strings at higher genus. So let's just look at flat space first. And as you all know, we have some kind of genus expansion for, say, the 4-point graviton amplitude, but be free to insert any amplitude you want there. And as you all know, and we know since the 60s, essentially, the first term in the series is the Virasoro-Shapiro amplitude, which essentially is like some ratio of 3 gamma functions up to some kinematical factor. But what's slightly surprising to me, at least, is that we actually don't know very much about the terms that follow in the series. So even at genus 1, there's already no analog of the Virasoro-Shapiro amplitude. So I thought since like this is not very told very often in string theory courses or something, I thought I'd briefly mention what are the problems. Why don't we actually know what are the higher genus amplitudes? there's not even a numerical result. So you might think, oh, we have like string amplitudes can be written, as you know, as like some integral over moduli space of Riemann surfaces, and then there's some integrand, genus G and and punctures, and these integrands, at least in flat space, are known very precisely, up to genus 3 or something. So why is it that we can't just throw this on the computer and at least generate some results and compare with other things we know? So first of all, so this was in flat space. Of course, if we're not in flat space like ADS, like we were talking before in Pedro's and Fernando's presentation, then we don't even know what are these integrands. So not even at genus 0, we really know these integrands. There are some special cases where we do know, but in general we don't. But other challenges that are always there, even in flat space, is that the integration over moduli space of Riemann surfaces, and sometimes you hear that you should compactify the moduli space of Riemann surfaces, is actually not convergent at higher genus. So even at genus 0, it's not convergent, but there is a region in parameter space where it is convergent, and then you can do some analytic continuation and get your Virasoro-Shapiro amplitude. But you know, it shouldn't be convergent because the amplitudes are supposed to have poles and branch cuts and all the nice properties that we know from S-matrix theory. So we don't want actually convergent integral. And what that means in practice is that you shouldn't actually, so this is a slight lie to integrate over moduli space of Riemann surfaces. What you should actually do is to integrate over a slice in complexified moduli space of Riemann surfaces. And that's necessary because in string theory, you don't have some I-epsilon prescription. In field theory, you have an I-epsilon prescription. In string theory, very few people talk about it because the worldsheet is usually taken to be Euclidean, but actually it should be Lorentzian. So from the point of view of worldsheet theory, what you should do is some kind of Wick rotation, and that leads to this complexified moduli space. So that's one big challenge, and nobody really knows how to, in practice, implement that, I think. Okay, for the open string, that's not too important. There are also several diagrams. You have to add them all. Only after that you get sensible result. Then we should actually do superstring theory, and there are different formalisms for that. It's not too important, but for instance, if you do the RNS formalism, that you should actually integrate over supermoduli space, which in general doesn't reduce to moduli space. So you actually have to do an integration over non-trivial supermanifold. And it's even unclear whether the measure that is on this supermoduli space is even well-defined for all genus. So even in flat space, I would say it's fair that there's not that much progress happening since the 90s, essentially. But you know, not all hope is lost. So let me make one very important observation, namely what usually happens, and we know by now that it happens from various other sources, like the ones Fernando was talking about, that the final amplitude, or at least the expansion of the amplitude in a low energy expansion, should be far simpler than the ingredients. So for instance, in genus 1, you need to integrate some theta function like integrands over moduli space. And so you might think that there comes, in the end, you should have all kinds of elliptic number theoretical objects. But actually, if you look at the expansion in Fernando's, well, he didn't actually write down the numbers, but they're very simple numbers. They're just rational numbers times some powers of pi. So they're much simpler than what you expect. So all of that, at least to me, is some hints that there should be some improvement of the formalism that doesn't go through the intermediate difficulties, but immediately ends up with some nicer representations of string amplitudes. So just some analogy I have in mind is that in field theory, for instance, we have by now many tools that do everything directly on shell, like the like for instance, we have the amplituhedron and things like that, that greatly reduce computational difficulty and make many properties manifest. Like also unitarity is something that is not manifest in worldsheet CFT. But still, worldsheet CFT is somehow the only tool we really have to compute from first principles all these things, at least until now, more or less. All right, so but also I want to mention that there are actually progress. There's progress happening, and let me just mention 3 areas where we have recent progress in higher genus amplitudes in string theory. So one is that there's ongoing collaboration of various peoples, mostly in well, by Doka, Fong, and Schlotter, or the Johansson, all these people. There's a, sorry for forgetting some names, but they systematically analyze the low energy expansions of these amplitudes. For instance, at genus 1, they have by now a very good understanding how to reproduce some numbers that appear also in Fernando's talk, how to reproduce them from the worksheet, like how to actually expand these integrands in a and the integrals in a low energy expansion. So there is great progress happening there, but it's very complicated, and so it's rather slow. Another area where we have big progress happening, I would say, is in de-instanton corrections. So until now, we only talked about perturbative corrections, but of course, there can be also non-perturbative corrections. And the Harvard group studied, so around Xi Yin, Victor Rodriguez, and Bruno Balthasar, they studied Sikh-Duan string theory. And in Sikh-Duan string theory, it's a nice situation because you know the dual matrix quantum mechanics. And so you can study these corrections. And they showed that you can compute de-instanton corrections in string theory explicitly and match them to the matrix model. And then later also Ashok Sen clarified some things about that, because there are some problems with normalizing the measure and so on, so it's not super trivial. And also Ashok Sen then went on to compute the de-instanton corrections to the type 2B flat space amplitudes, and they also match with what's known in the literature already, which was basically found from imposing S duality and various consistency conditions. So I think that's a very promising direction. And another thing is that in that work of myself and Bob Knighton, you can in ADS3 CFT2, there's a special case of ADS3 CFT2 where we also know the full duality, very similar to the Sikh-Duan string theory and the dual matrix quantum mechanics. And they are actually, it has a very simple, it has very simplifying properties. So the most simplifying property is that the integral over moduli space that you have to perform is actually not a real integral because it localizes in moduli space. Because of that, the integral is almost trivial to perform and reduces to a finite sum, actually. And because of that, you can just directly match the all genus correlators between the string wordsheet theory and the dual CFT2. So that is also one area where we have progress, but of course it's a very simplified arena. So that's essentially what I wanted to say. So I'm happy to discuss. Thank you very much.
Thank you, Lorenz, and thanks to all the panelists for these introductions. So what I would do now maybe is to make a couple of comments that just popped into my mind from listening to your presentations, and put on the table a couple of questions, maybe slightly provocative, and then you can just try to address them in whatever, you know, like in a very free-flowing way. So a couple of things that sort of struck me is the fact that from Pedro's presentation, I got the impression that there seems to be some hope that we can understand something which is a little bit chaotic inherently from integrability, which seems something that is very rigid on the other end. And this is a very intriguing possibility, but there seems to be also some tension between this concept. Of course, Pedro gave us some idea of how this might be resolved. I mean, the notion of essentially this tessellation and doing the trick, but at the price of pushing the complication a bit to the sums. So that's quite interesting. Another thing that I got a little bit from Fernando's and the Lorenz presentation is that, in a sense, it almost seems that sometimes some things look under better control, perhaps even in ADS CFT, that they look in flat space, maybe because we have access to this, you know, different set of tools and duals and tricks. And it seems to me that at the end, even the examples that Lorenz gave, they exploited some simple duality to really do a lot of progress. So it's a bit of a question of, you know, like the difference between some object that we can describe or define in principle for any string theory and the mileage that we can get out of holography or dualities in a broad sense. Then I have a couple of more general questions. One is the obvious one, which is, how far do you think we can push all these ideas? And the other one, which maybe is a little bit provocative, is suppose that we are extremely successful and we understand non-planar corrections to some amazing extent. For some observables, we even resum the genus expansion. We have some, for instance, we understand n equal 4 superior means, let's say, to an enormous amount of detail, even in the non-planar limit. What do we learn about real-world physics, such as quantum gravity? So these are sort of the ideas that I would like to put on the table, and if any of you wants to jump in and like open up the discussion, please go ahead.
Let me make one point that I think is important, that in ADS CFT, I mean, it's not that we can compute, for instance, in the example I was mentioning, and similarly at seq-to-1 string, it's not that we have any hope of computing, I think, all higher genus or Dean-Santon corrections or something like that. But we can just show abstractly, essentially, that they agree with the dual matrix quantum mechanics or CFT2. But even in the CFT2, it's not that we can compute it. So it's just essentially a reformulation. I'm not saying that you can like explicitly write down some result. So I think that's an important distinction. It's not that we. Yeah.
Another comment I wanted to make, just because Lorenz has commented on that. Something that we are missing on ADS. So on one hand, we can use the ADS CFT duality, and we can compute correlators in the boundary, and we have n equals 4. And I think, at least in my perspective, it's like n equals 4 gives you what the definition is of quantum gravity on ADS 5 x S5. Very much like what is M theory, we don't know, but M theory on ADS 7 x S4, etc., is the 62,0 theory. So that's an operational definition. But we don't have a first principle way to compute amplitudes of a string theory in ADS. We don't even have the vertex operators. So very much like Lorenz is saying, I mean, we do have some structure, and then we can match this structure to the structure that we expect, and we can take some flat space limit, and we can compare this to flat space. But still, it would be beautiful to develop some kind of like strings on ADS from first principles. And yeah, but I think it's still like computations in flat space from the string theory perspective are on much better footing than ADS. Simply because in ADS we don't have a prescription. We don't know the vertex operators. There is a lot of things that we don't have in ADS.
Yeah, if I may briefly respond. So one important thing also, I think, so in principle, I think perturbatively, we more or less have could formulate string theory in ADS. So certainly in ADS 3, where I focused on, so there perturbatively is very clear what you should do.
Yeah, ADS 3,
but, yes. But like one very interesting point to me is that if you go to the non-perturbative regime, string theory is actually not very clear what you should do. So you should maybe, for instance, in the seq-to-1 string, it turned out that you should include some Dean-Santon corrections, but not other ones to get a consistent theory. But then you might also worry about like including other geometries, other backgrounds, or things like that. Like, so their string theory really starts to be not uniquely defined. And then, as you say, the dual CFT is like a non-perturbative, nice description, and that just defines it.
So maybe a question to Pedro. The approach that you described seemed to be inspired a little bit from the string worksheet, even if it also gets some intuition from n equal 4, but it has to do more with the perturbative corrections related to what Fernando and Lorenz were describing, right? Can you comment on this?
Yeah, that's true. So I think basically whenever you have a quantity that you want to compute, that you can draw a string, you can use integrability. As soon as you don't know what the picture is in terms of a string, you cannot. it doesn't mean that it needs to be perturbative. If it's some kind of D brane where the string attaches to the D brane and so on, that could still be a computable effect. So I think some non-perturbative corrections, as soon as you can draw them as a string that is coming out of some instanton and going somewhere and so on, then you should be able to compute it. But if it's not a string picture, if it's a black hole absorbing something, which is not something that you draw as a string, then you cannot compute with integrability. So for at least right now, I think this is what is conservative to expect. If you can draw a string to compute the process, it's integrability. If you cannot draw a string, like a black hole absorbing something, then it's not an integrable quantity. But let me just make one small clarification that I'm not claiming that we can use integrability to study chaos. I mean, 1 over n, each term in the 1 over n expansion, we don't expect to have chaos there. The chaos would be, again, for quantities for which you would really need to resum the 1 over n corrections, take into account all the non-perturbative terms that are very important there, and so on. If you ask me, is there any chaos in studying 4-point function of 20 primes at genus 2? No, probably not. It's probably not chaotic. It's so resumming all these corrections will be very interesting, but I'm not sure we will learn about chaos. But yeah, let me also make one other trivial comment, which is, of course, we have integrability for the 2-dimensional worldsheet. That means that the 2-dimensional worldsheet theory, particles scatter in a very trivial way. A beauty of using integrability for studying 4D gauge theory is that the 4-dimensional scattering is by no means trivial, right? So that is still very interesting, and that the theory is integrable. That means the material is very special, but then the way we glue the material and the outcomes of doing all these sums and so on, they have all the rich structures of scattering amplitudes in higher dimensional theories. Let me speculate. Let me say, what could be one application of all this business if we could indeed solve n equals 4 super young Mills? So, and again, I'm speculating, but one of the reasons that one of the possible applications could be that perhaps we could understand more kind of on-shelf building blocks for string theory. So as Lorenz was explaining, often we do all these integrations over moduli space and so on, or partial integrations over moduli space, and then results turn out to be much simpler than what we have. And for example, these hexagon patches, to me, the way I think about them is that we have the integration over the moduli of the string, and most of that integration is done. And you are left with a discrete set of summation over a discrete set of options, which in the case that Lorenz explained in ADS3, sometimes it's everything there is. But here it's at the end, you get this discrete sum, everything else was done. All the tension part of the string break and so on, all that was done. And you were left with just a little bit of discreteness of summation over the moduli. And then this hexagon is the fundamental object that takes care of that last bit of integration over moduli. It would be great if the hexagon could be more generically a definition of string theory. If we could say that any string theory can be decomposed into hexagons, and defining string theory is about defining these hexagons. And okay, that's a dream. But if this could be true, then instead of thinking of the fundamental building block like people think in string theory, which typically is the pair of pants and so on, it would be the hexagon. And then you would use the hexagon, try to find what properties it should have, and forget about worldsheet theories, forget about worldsheets and CFTs that often are very hard to study, and you would go and bootstrap hexagons. So that could be a possible outcome of learning very well how to deal with these hexagons in n equals 4.
So maybe I have a comment. One is that, and people that have managed to listen to my talk, which was in the middle of the night, for some of you might have heard this. So I think it will be extremely interesting, and I really hope to manage to look at this in some detail, to compare this hexagon picture with the ADS3 RNS string picture, because as Lorenz was saying, that picture is perfectly well defined. It's unlike ADS5, where the string worldsheet and the vertex operator and so on are a little bit tricky. There everything is well defined, so you would have like two in principle well defined approaches, and you could see exactly how they fit together. So that's very interesting. The other thing I just wanted is maybe a little bit of a technical point, but I find it very interesting, something that Pedro mentioned. So whether like at a fixed genus, let's say genus 2, if you study something like, you know, the correction to the spectrum in n equal 4 superior means, you expect or not to find chaos. So Pedro was saying that you shouldn't expect, and I wonder, because I see Anne Spiering in the audience, and I know that she, and also Tristan McLaughlin, they're both in the audience, and I know that they have been working on this numerical study of chaos. I think that they were working at fixed n, but I wonder if they can comment on whether, you know, they have encountered this difference between fixed genus, if they have some.
But let me just clarify, sorry, one thing.
Please,
of course, it would be much better to hear from them, but I did not say that the spectrum should not be chaotic. I just said that if we look at the theories from the point of view of the traditional point of view of spectrum, Hamiltonian, and so on, of course we will find chaos, because of course we will have these long range effects and so on. So of course the spectrum is chaotic. I'm saying that if you think from the point of view of the world sheets, then you can describe that those chaotic spectrums from using integrability. But the spectrum, of course, should be chaotic, and they showed that as expected it is chaotic. Okay, but I will let them.
Understand correctly that the chaos, you would say, would come in the resummation of the 1 over n effects, like not order by order, or would you already expect it at leading order?
But of course, sorry, but of course, all these sums are very asymptotic sums. All these 1 over n.
Border resummation or some sort of, you know, appropriate sense. So I guess my question is, I completely agree. I think it's clear that at finite n, if you do some finite n computation n equal 4 superior means, you will find chaos. I wonder whether if you do so you don't have chaos in the large n result for the spectrum. I guess I wonder whether in the corrections, in some sense, you would expect chaos already just by incorporating the first order correction, or whether it's something that only would appear when resumming the expansion.
So what? Sorry, so a silly question. How would chaos manifest in the spectrum? Let's say at order 1 over n. So if n is equal to infinity, you have some discrete spectrum which is not chaotic, and I guess 1 over n corrections would just start splitting this, but the split will still be of order 1 over n. So how would you really see chaos at 1 over n or 1 over n squared? What would
I think that the study that Tristan and Anne were doing is really at the level of the distribution of the spectrum, because different type of systems, depending whether they're integrable or not, have a different type of distribution of eigenvalues.
That's finite n,
yeah, but that's a finite n.
Yeah,
but at 1 over n, you never can see, right? So there is some infinitesimal split around the pre-theory values, and that's it. Like I cannot see how anything else at any order in 1 over n. So but sorry, maybe Tristan. Maybe
let's hear from.
Can you hear me? No. Yes. Oh, okay.
Yes, we can hear you.
Okay, I just wasn't sure. Yeah, no, exactly right. The only thing I would say is that we didn't need to include non-perturbative effects. So we were looking. We didn't need like exponential effects. You could see chaos already, sort of with. Yeah, like in the perturbative expansion, but indeed it needs to be at finite n. I mean, yeah, it's just like you say, if n is infinite, then what's perhaps also interesting is that if n is large, but finite, like where do you see the crossover from integrability to like chaos? And of course, there is a way of characterizing, as Alessandro was saying, you look at the distribution in the spectrum, and there's a characteristic distribution for integrable systems and one for chaotic systems. And you can ask, at what value of n does the system genuinely cross over? And I don't actually have a good answer to this, but I think there was a paper by Poshke and Takash who looked at sort of a crossover not in spin chains and other integrable systems, and you can actually see, depending on sort of whether the chaos is whether the system is weakly chaotic or strongly chaotic, the sort of chaos appears differently with the length of the spin chain. And if I have to say, I think essentially chaos appears with the size of the Hilbert space. So that would be the only thing I would say, is that the larger the dimension of the Hilbert space, the quicker you see chaos appearing. That would be. So I think that's the relevant thing, not the size of n per se, but the size of the Hilbert space.
So the sort of the R charge of the operator in the n equal 4 language, that would be more or less.
Exactly. Yeah. In that
speaking.
case, yeah, that's right.
Let me add something related to what to your comment, Alessandro, about ADS3. I totally agree. I think that it would indeed complement what I said. It would be very nice if we could bootstrap these hexagons for a general string theory. But if in a given string theory we could really have a sharp definition saying this observable in the worldsheet is what the hexagon is, that would be much better, right? Saying it's this particular twist operator with these boundary conditions, blah, blah, that is the hexagon. That's the definition. That would be great. And maybe it probably ADS3 would be the best place to try because it's under much better control. But let me also make a comment about n equals 4 in that regard. In n equals 4, there is something happening with that it happens really a lot. So the hexagon, as we said, is an expectation value.
For me, you are breaking up a little bit. Can you repeat the comment about n equal 4?
Okay, sorry. Yeah, I'm in an Airbnb in Rio, and yeah, my conditions are not optimal. You can probably hear some music outside as well, but it's like a disco. I mean,
it's okay. We'll just ask you to repeat if it's unclear.
Okay. Yeah, the modem is there, but so I was making a comment about n equals 4. So in n equals 4, we have this hexagon, which you insert a complete base of states. So it wants to, as input, to ask you what states you put, and output, it gives you a number. And what are the states in n equals 4? They are a bunch of scalars, derivatives, and so on that correspond to string excitations of given polarizations and so on. And now what I'm going to say is rather technical, but these scalars and these derivatives and so on, they transform under a symmetry group of an SU2/2 squared. And so you can, when you expand them, you can give them two indices, one for an SU2/2 left and one for an SU2/2 right. And so you can think of each particle as like a meson that has one index of SU2/2 left, one index of SU2/2 right. But the particle is like the scalar. There is no quark and antiquark. You cannot separate them. But that's precisely what happens in the hexagon. In the hexagon, you take these particles apart, you separate them, like you do some kind of fractionalization, and now you have the quark and the antiquark. You take them apart and then you scatter them to get the hexagon. So it's a technical thing. It's kind of a fun observation. But my understanding was that this kind of fractionalization and this kind of splitting of degrees of freedom is something that is showing up in some recent proposals of Gopakumar and Gabardial, where they were trying to propose a free dual for n equals 4 super-Young Mills. And they find some kind of, they also seem to be going in the direction that in the free theory, at least, the degrees of freedom break up like that. And so it would be very nice also there at weak coupling to try to see if indeed their hexagons would come up more naturally than in other approaches like pure spinor and so on that are better suited for strong coupling.
So, maybe I can say something about that. Well, yeah, I have actually one comment and one question. The comment is that in the proposal of Gopakumar, so the breaking up of degrees of freedom in left and right, that happens before gauging. So they have some kind of some BRC cohomology they have to introduce. And once you, like before the cohomology, you have like some standard, or not standard, but some worldsheet CFT, and it has left, right degrees of freedom. And then you impose some gauging, some BRC cohomology, and then basically only like the diagonal degrees of freedom survive. So that's how the gluing and separation works. And the question I wanted to ask you about hexagons is, why is there no hexagon for flat space? Wouldn't it be the simplest thing to like construct flat space hexagons and match them with flat space worldsheet theory?
Yeah, I agree. So indeed, I tried a little bit and failed. So I think one obvious thing we could say that there is a difference between ADS and flat space that makes ADS a little bit simpler is that in ADS, the excitations of the string are gaps, and in flat space, they are gapless. So what I mean by this is that if you have a string in flat space, the modes of the string, you can think of them as massless particles free massless particles in 2D. They just move to the left or to the right, and they are massless, and you can put any number of them. In ADS, at least when we light cone gauge fix, because of the centripetal force of the strings around where we expand about, they do get some mass. They acquire some mass because of the centripetal energy. And so in ADS, this gluing of the hexagons, there is it's much easier to glue because you are dealing with a gapped system, and you can really label the states by energies and say that first I have the vacuum, then I have mass 1, then mass 2, then mass 3. And there is a hierarchy of importance of states. And when, in particular, when the string becomes big, you truncate to the lowest states. That's much more complicated when you have a gapless system, where in principle, you really need to do all these sums. So you would have to define the hexagon, be really, really confident that you defined it right, resum all these infinite sums, you would not be able to truncate them, and then see if you could reproduce the final result. So I think it's the lack of having an intermediate step where you could take the big operators and see if you are on the right track that I think technically, as for I tried a little bit. I mean, I agree with you. It should be done, yeah.
So
but
I have maybe a couple of comments on this. Yeah, I think that so one is about the factorization. Indeed, in the story of Gaberdiel and Gopakumar, it does appear, but it's not completely obvious to me how fundamental it is. I mean, it appears in a very similar way as it appears also in integrability, really from the sort of representation theory of n equal 4. So, and related to this, I wonder, and I tried, and speaking of things that we tried and failed, I tried and failed to extend this hexagon approach to ABJM where there isn't this factorization. So it's not obvious how to do that. And to date, it's not clear to me whether this is like, you know, a technical issue, the fact that for ABJM it's not possible to write a nice ansatz for this hexagon and generalize it to an n particle form factor, or whether it's a fundamental problem. So that's sort of one thing that I still don't quite understand. And then one last comment: this fact that you have massless excitations, unfortunately, is something that you would also have in ADS3, especially in the case where you can make contact with the RNS string. Essentially, the type of spectrum and the S matrix is pretty much the same as flat space. So I think that the problem, flat space or IDS3 without Ramon-Ramon fluxes, they are extremely similar problems. So I'm not completely convinced of which one is easier. I guess you get a little bit more control in ADS3 because you can try to approach this limit of pure NS of no Ramon-Ramon flux by having Ramon-Ramon flux and tuning it away. But yeah, I agree. I also looked at some point at the flat space hexagon, but yeah, I think the same confusion probably that Pedro had also stopped me from going much further. Yeah.
I had a comment. Oh, sorry.
Yeah, sorry. Please, I was just about to say that I wanted to invite Fernando to say something, otherwise we monopolize the thing. So.
Yeah. No, yeah. I had a comment and a question, and you telling about ABJM made me remind that. And one thing is that in the kind of both using localization and the conformal bootstrap, we see that all maximally supersymmetric theories are on the same footing. And by that, I mean ABJM, n equals 4 super Yanni-Mills, and the 2,0 theory. However, two of these theories are not dual to a string theory, but are dual to an M theory. And so one wouldn't expect maybe an integrability there. However, when you look at the results, they seem like very much on the same footing. And I wanted to ask whether, like, what is the opinion of Pedro and Lorenz and Alessandro, etc., of whether we have some hope. Of course, the theory wouldn't be integrable, but perhaps if we look at that, like a given family of observables or on a given regime, I don't know, like whether this kind of integrability, and ABJM is a good example because there shouldn't be a string theory description. Well, that's not fair. So there could be a description. It depends how you do with K and N, etc. You could have a description that interpolates between a string and M theory. But for sure, for the 62,0 theory, there isn't. And yeah, I wanted to make that comment and to see the views of experts in integrability.
Yeah, let me make one comment. So of course, ABJM, you're right. So there is a limit where it's type 2A. So then there it's the usual string here. Let me just make a simple comment, which is that often in gauge theories, whether they have a string theory dual or not, there are quantities that are string-like, right? So flux tubes, for example, and
yeah, but 60 is not gauge though. The 62,0 is not a gauge theory.
Yeah, but maybe some. I would, yeah. What's the behavior in that? There is a family of twist 2 operators there as well, right?
Well, yeah, you can, well, at the strong coupling, you would start at twist, so higher twist.
Yeah, but not at strong coupling. At finite coupling, there is a family of twist 2, right?
I see. So you could, well, there is not such a thing.
I wonder what.
Yeah.
No.
There is not such a thing as weak coupling.
Yes. Mm-hmm.
So we don't have like a perturbative limit. It's always strongly coupled, and the only parameter is n, which is the number of n fibranes. It could be amazing if one would have this flux tube picture, or some, yeah.
No, then I don't know about the 2,0. It's not integrable. Right? There's no string. There's no integrability.
Yeah.
Lorenz, do you have a comment as well?
I don't really have anything useful to say, so I won't, I think.
It's all right. It's all right. So I was
maybe
can
I make a comment?
Please.
Let me say there's something very interesting in many of the things that Fernando and others have been doing in the analytic bootstrap, and there are two limits that, as far as I understand, they can normally make great progress in. One is large n, and the kind of expansion in 1/n that Fernando was discussing today. The other is large spin and some expansions around some no limits of correlators and so on. And maybe one thing that would be interesting to explore a little bit is the interplay between the two. And this is precisely related to this physics of flux tube, that sometimes, say, some physics is dominated by some long flux tube, some long rotating string that is rotating. But if the spin is really, really huge, eventually the string breaks, and now you have two strings that broke up, and now they behave more like two planets that are far away. And so there is some interesting interplay between a large spin, but how large, and large n, and the non-planar correction. Maybe I'm not very precise would be to try to say something about bootstrap. And I know that Fernando has some work in that direction with Sasha Shibaedo, but my understanding is not very systematic yet.
No, indeed, yeah, and I fully agree. I think that is a super interesting question, and questions like level crossing and I fully agree. And I don't know. I think it's hard to understand. It's a hard question, but it's a very super interesting question. Indeed.
So I was wondering, since we have also many experts in the audience, whether anybody from the audience, either in Korea or just online, would like to also make some comment or ask some question on the discussion. Maybe we can open it up a little bit.
So I have a question for maybe Pedro and also Fernando. So Pedro have been working on integrability and Fernando on bootstrap. So I want to know, is there some intersecting point where the two approaches can work together and help understand each other? So maybe you can comment on that.
Yeah, I personally have been exploring this corner of bootstrap and large spin operators. So there was a beautiful paper by Fernando and Agnès Ebisi about 4-point functions at large spin. And for example, there they predicted that 3-point functions of two scalars and one operator, a very large spin, which is you can think of it as a spinning folded string, as a very sharp coupling, finite coupling dependence. And that came mostly from the bootstrap, plus some logarithmic scaling and so on. So that's, for example, a very sharp prediction for integrability. And I could explain why that quantity is still a little bit harder to compute from, too hard to compute from integrability, but there are other cousins of that quantity that we have been exploring more recently that are on the same type of footing, same universe of quantities that I think integrability will be helpful to compute. So I think this is a good corner because this light cone limit of correlation functions, what happens is that when points are null separated, they often dynamically generate a long string. So if you have 2 points that become null, the operators that dominate when you make an OPE around these null points often become some null extended objects, some null strings, some flux tubes. And so even though you start from, and on the other hand, these configurations where they become null because points are approaching are precisely the points that the bootstrap can study, because the bootstrap is about OPEs. And so that's a good corner. So on the one hand, you have bootstrap control because points are becoming null separated, so the resistance are going to 0, so the OPE is very good. On the other hand, because it's a non-local object, it's a long string, and therefore integrability should be very helpful to study. So I would say that it's a good point of intersection. It's this analytic bootstrap of large chain operator, and I think there is a lot to be done there.
Yeah, I don't know much to add. No, I think, yeah, Pedro made an excellent point, and I think he was the one that made the biggest progress in trying to combine these two things in the world. And perhaps something that would be interesting would be related to the discussion in the 6D 2,0 theory, would be to try to study correlators which are null separated and see how much progress, correlators of local operators in the limit where they are null separated, and see whether they admit some nice description in that. And I think that would be exciting. It's not a gauge theory, but on the other hand, perhaps some of the, there is like similar structures or something. And I think that could be a nice thing to study for it.
Yeah, I agree. That would be very interesting.
Yeah.
I see. So actually related to that, also about the large swing limit. So work together with Jota and Eduardo, we had this determinant-like operator. So it's a D-brane attached with a string. And there we can also take the large swing limit of the single trace operator. And we have seen some interesting behavior in that limit. And we believe that some perturbative results should be possible to obtain. It will be something like the cusp anomalous dimension in the OP coefficient regime. So then the question is, can we have some predictions from the bootstrap for this determinant-like operator in the large swing limit? So you take determinant and then can you consider this OBE and then take the large swing limit and give some predictions. So far,
I think Frank and Shota, maybe with some other collaborators, they were thinking about the problem. Yeah.
So is that like a generalization of like a form factor kind of computation, or your sound was going in and out, so I didn't get. So it's like a determinant operator.
Yeah, I think it's like analytic. It's like a defect CFT,
right? Where
the points in the bulk are approaching a null limit, and in CFT they are ordinary position.
Right. Thank you. I see.
So perhaps I have another question. In the meantime, if people from the audience want to think about other questions, they are welcome to. And it's a bit of a broader picture question, and it might be maybe even too broad, but there has been some activity motivated by studying JT gravity in these very, very nice low dimensional models. Some activity in understanding the factorization problem for the partition function in holography. And I was wondering, so this of course is something that is under control in this very specific setting of JT gravity, but Lorenz also I tried to address this question in the very specific setting of this ADS3CFT2 simple point of the modulus of the parameter space. But in general, do you think that this is something where the techniques that we have been discussing can give some insight, or perhaps the thing is just too non-perturbative, or maybe as soon as you can use any of these techniques, you will always find something factorized anyway. So do you have any take on this?
Okay, perhaps I can comment. My take in general is if we are discussing these stringy kind of correspondences, like ADS5 S5, or I mean, in the ADS7 times S4, it's probably it's the most clear situation we can have, because there's only one single candidate as a dual theory. There's no other candidate. So there's nothing you can even average over or do something like that. So in these cases, it's almost, I mean, it has to work, I think, that you get like a single dual without averaging or anything. So you should really have a clean ADS CFT correspondence. And all the quantities that have been computed so far seem to indicate that as well. But yeah, so my general suspicion is that whenever you have like a nice stringy dual, maybe you need it to be integrable, or you need it to be have enough supersymmetry. I don't really know, but then you should have like a clean dual CFT, and I think there's nothing wrong about the correspondence, and that's all we know so far seems to indicate that. But if you start with some semi-classical theory of gravity, like JT gravity, or I mean, JT gravity is really, I think, the only kind of example we know. I mean, there are other dilaton gravities in 2 dimensions, but even going in 3 dimensions, you already don't know how 3D gravity should be really defined. So it's not even clear whether it does exist. Maybe it does, maybe it doesn't. There, it's not clear what you should get as a dual CFT. Should you get an average, or does it even make sense, and so on. So in 2D, it seems like maybe it's even an accident that there is this kind of correspondence, because it's like some kind of remnant of the minimal string matrix model correspondence, if you want. So I'm not sure whether in higher dimensions in stringy correspondences, we should have these ensemble averages. Maybe in some kind of effective correspondences we do. That's my rough take on it.
So maybe somebody else has more comments, but it's also interesting if I want to play a little bit devil's advocate, because then it's not completely clear whether, maybe we are quote unquote wasting time doing ADS-CFT or stringy correspondences in general, because it might be that after all, this dilaton gravity, which is of course very spatial and 2-dimensional and so on, it might actually be closer to real world gravity than strings are. So of course there is a question, right, whether what is the nature of quantum gravity. And I think that there is generally an understanding that the string theory captures a lot of features of quantum gravity, even if maybe not everybody would agree that the real world gravity comes from some sort of string theory. So I don't know. How do you feel about this? I think it's a bit of a broader question, but let's have some fun with it.
I don't think you would find many people that would say that these 2D gravities are closer to the real gravity.
I mean,
I think it would be quite a lot. I think it would be hard to justify that claim. I don't know. I think real gravity has gravitons.
And it's consistent quantum mechanically, and it's in higher dimensions. And
maybe I can also cite Wafa here. So if Wafa would be in this chat, he would tell you that in like 3 dimensions is maybe a bit special, but 4 dimensions, there's nothing like pure gravity in 4 dimensions. And there's the string Lampos principle that basically says that everything consistent starting at least in 4 dimensions should come from string theory. So that's one of the conjectures of the swampland program. And it's true that all the evidence seems to point to that fact. So in that sense, Alessandro, I would say to you that at least for real world gravity, I think everything should come from string theory. That's the common wisdom in the community, I think, right now.
I don't think we have any loop quantum gravity people in the audience that can comment on this. So speaking of the audience, any more questions? So we went a little bit far field here, but maybe we can bring it back a little bit to the original topic if somebody has some more questions. Any more questions?
If not, maybe we can address also one of the initial questions of Alessandro, which was what can we actually learn about quantum gravity if we're able to compute all these non-planar observables, which I think is actually kind of the most important question that we haven't addressed yet. And I think my take on it would be that basically we're collecting data right now. We're collecting more and more data points. How can we compute? And we're getting we are always finding that the final result is easier than what we thought, almost always. So it seems like there's some kind of hidden structure that we don't know yet. And we're basically collecting data points. And at some point, the hope is that we find some kind of new description of string theory, M theory, whatever. And that kind of is extrapolated from these data points. And then we would learn a lot, of course. So that's at least my hope, how this pans out and why it's useful to do what we do.
Yeah, and then if you consider like this, for these specific cases, these theories, like these non-gravity theories, these gauge theories, are by definition the quantum gravities on those backgrounds. So you would be understanding and solving quantum gravity on a specific curve backgrounds, and that's pretty good. And like, yeah. And recall that this 1 over n it maps to the Planck length, etc. So if you are able to resample that, then that would be beautiful, right?
But to me, there's always one mystery. Maybe you have a take on it. Is if you start with these different theories like ABGM, ADS 5 times S5, and so on, and you take the flat space limit, then you should always get the flat space result. And there's probably no reason why these super different looking gauge theories, or not even gauge theory in the 2,0 case, somehow should have the same flat space limit. Is there any kind of understanding why that's the case?
Yeah, no, I mean, like at genus 1, you can see how things work mathematically and why you always get like back to 11 dimensions in both cases, and 10 dimensions in the case of n equals 4 super Mills. But yeah, but it's quite interesting. But I think my feeling, my take is that when you just take the pure flat space limit, then you are just seeing, let's say, the number of dimensions. And then the least flat space, when you take like corrections to the flat space limit, then you start seeing the structure of the background and all that. So you get some universal, and then are corrections to the flat space limit, the ones that start being different for different theories. And this will tell you what different backgrounds you are having, etc. And yeah, and that one can see in, for instance, comparing the 2,0 and ABJM is quite nice because these are very different looking theories, but it turns out that when you do the genus 1 computation and take the flat space limit, the answer is the same, which is the box function in 11 dimensions. That's super nice. But then corrections to that like look very different in both cases. Yeah, but yeah, but it would be nice to have like a better understanding and this.
Maybe can I ask a question as well? So, and I guess there's this thing about the flat space limit and the hexagon, and trying to sort of generalize it to string theory. And in some sense, as you were saying, the flat space limit is sort of not a good limit, but you can just take string theory in a plane wave background, right? So this should be a consistent string theory. You can study higher genus corrections. It's a well-defined conformal field theory. You have conformal field theory of higher genus surfaces. And this should be well-defined from the hexagon point of view. Easier in some sense, right? Is that a sensible thing to look at? Yeah,
I agree. Maybe then you have some twist operators for some free massive bosons, right? At least to start with the bosonic sector. And indeed, a nice question would be, how can I formulate 4-point functions in the BMN theory as in terms of correlation functions of these twist operators? Yeah. So let me mention something obvious that for some people might not be so obvious. When we cut surfaces in these hexagons, it's a bit unorthodox way of cutting. Typically, we think of cutting more in an OP sense, that you have some incoming states and then you make a sphere around these states and you cut them like that. This way of cutting with hexagons and triangulations, you cut right across the states that you insert. So if you have like two vertex operators, your cutting line will go from one vertex operator to the other, which is exactly what you would not think of doing if you have some worldsheet with a bunch of punctures. You will start drawing circles around the punctures, so not lines between the punctures. But that's exactly what you do. You start drawing lines between the punctures, you triangulate the surface, and so you really, so in integrability, we made a guess for what it means to cut the state in two. If you have a vertex operator and a bunch of dashed lines going there, we could have some intuition about what it could mean at the level of an excited state, because if that state is a string and there are a bunch of excitations moving in that string, when you cut, you should just say, oh, the excitations can end up in any of the piezo slices that I decided to cut my string at. Now, if you have a general string theory, which doesn't have such a clear picture of a number of excitations being fixed and so on, understanding what does it mean to break a vertex operator into a few slices would be a challenge that we'll have to address. In the BMN theory, probably not. Probably in the BMN, you have, again, a bunch of excitations and they scatter freely. So it sounds very much doable, yeah. We did a little bit of, we have some in our original hexagon paper with Benjamin and Giotto, we had some comments about reproducing some aspects of the BMN objects, of the objects that people studied when they were studying the string field theory on BMN. We pointed out that indeed, many of the objects that people had, you could rewrite in different variables and they do look like the expectation value of some hexagon twist operators and octagon twist operators and so on. And Romold-Yannick and Bagnac, they also pointed that out, that some previous, so I think people that know that story well should definitely try to do it. I think that's very promising.
Yeah, here I think actually the work is for people who work in conformal field theory. We can you can almost say, string theorists need to go off and do this calculation, right? Because you actually do have a definition already. In some sense, it's almost waiting that if someone could do this conformal field theory calculation, you should be able to.
Right. Yeah, so you should be able to take that 4-point function. There is a bunch of free bosons, right? And you decide to cut your worldsheet not in the conventional way, but across vertex operators. And now that should define for you that the way to do it is introducing some twist operators, and that those will be the hexagons. I agree with you with that.
But that is after doing the moduli space integral and so on. So it's not super clear what the relation is. Like it's not that you actually cut in a CFT like that.
No, I would say it's before. I would say the integration over the moduli
is like the sum in the hexagon.
There is still a sum in the hexagon. So when you have these triangulations, each line of the triangulation comes with an integer, and you still need to sum over those integers associated to each line.
But of course, in an OP, you also have to do the full sum. Like you need to sum of all descendants. So there you have a sum, and then you also need to integrate over module.
Right.
The descendants
so
you would
here
have
we don't have
the hexagon. I mean, like all these mirror particles, you have everything right there. But I guess one difference is that the physical particles are on shell in the hexagon, right? In principle, the formalism works when
physical ones, yes, the mirror particles you integrate over. So the mirror you integrate over. So you would cut. So you would have in the BMN theory, you have just massive free bosons and fermions, right? And so when you cut, it's a 2D quantum field theory of free massive bosons and fermions, right? So you cut over the dashed line, you will insert on that dashed line a complete set of states. So you'll have vacuum, 1 boson, 2 bosons, 3 bosons, and so on. And that's in one of the dashed lines, the same in the other, the same in the other. And now you draw a triangle, and that's the hexagon. Now you have to understand, well, what are the boundary conditions at these cusps and so on? What should you do, as Tristan was pointing out, how to define it properly in the CFTs so that this makes sense and it's not just a cartoon.
But it's not really the CFT of a plane wave background, for instance, is not a free CFT. Like if you're talking about the worldsheet CFT of a free plane wave background, is a very complicated CFT. Like only if you go to light combination or something, then you get a simple kind of theory. So the relation between the CFT. Yeah, that's my point.
I have in mind the quantum field theory, the light cone gauge quantum field theory, not the CFT.
Yeah, that's right.
Yeah. So even better would be to do it in the language of the CFT.
That's actually one of the reasons I think it might be interesting, right? That you know that the result does have to be simple, actually, right? There's a gauge where it's simple, but and also it's well defined. But indeed, it looking at it as a CFT, it's a very like a non-trivial CFT. The only issue or not the only issue, there's lots of issues, but one thing, of course, is that you would have remote backgrounds, and so you probably can't use RNS formalism, and then you need to use, I don't know, like work of it for just maybe.
Yeah, actually, I studied this a couple of years ago, and like the only result we managed to get after like a huge amount of technicalities, you can in ADS3 there's a formalism that deals also with Raman backgrounds, and you can compute the BMN limit spectrum of that. But it's complicated because it has like square roots in it, which is something you don't usually have in CFT. So the worldsheet theory spectrum is kind of complicated. Of course, the light cone Hamiltonian spectrum is easy. And like we were able to get that, but in a kind of complicated way. So it's not like it worked, but it was not really like really useful for anything.
Is that with the formalism of Maldacena and Oguri, or?
No, Maldacena and Oguri is for pure SNS only, but there is a formalism of Berkowitz, Waff, and Witten that's sometimes called the hybrid formalism, and that works.
The hybrid formalism.
That worked for RR backgrounds as well.
Thank you.
So in a sense, flat space strings or pure SNS ADS3 might seem like a better place from this point of view. And there is this problem from the point of view of integrability that you have essentially relativistic or almost relativistic massless particles, but at least for the spectrum of ADS3, what happens is that in principle, we would be very worried about having all these light particles and having like finite volume corrections that are super dominant, but actually everything drops out. There are lots and lots of cancellations, which in a sense are expected because the CFT predicts a spectrum which is very, very simple, extremely degenerate, much more degenerate than ADS5. Yeah, I have high hopes that basically the same will happen also for 3-point functions, that you would have like all these, in principle, very dominating integral that involves massless mirror modes, but at the end, actually, most of it drops out. That's that I think is something that more or less has to happen if there is any hope of reproducing the CFT answer.
The other option is that you have infinite sums, but you do them, right? Not all infinite sums are hard to do, right?
Yeah. That's certainly a possibility. Yeah. The thing that is a bit tricky is that you cannot just truncate to a certain number of mirror. So now we're getting a little bit technical, but as the experts know, in ADS5, you typically can do no mirror particles or maybe one mirror particles, then you do two mirror particles, and they're sort of in the weak coupling expansion. They come at different orders, at least for 3-point functions and some simple 4-point functions. Once you start having these massless guys, any number of mirror particles has to be considered in one go, essentially, which makes things even more complicated.
I mean, let me just mention for everyone, like the result is not completely trivial. It's an interesting result. It's kind of like the DOZZ formula. It's very similar to that. So it involves this upsilon function and so on. So it's like slightly non-trivial, but not completely intractable. So it's kind of a sweet spot.
Nice.
So I think we have been at this for like 1.5 hours, which sounds very good. I think maybe we have a few more minutes for some last questions and comments. Again, if there are questions and comments from the audience, I think it's a good moment to make them.
I have a question. Can you hear me?
Yes.
Okay. Yeah. So people, especially Lorenz, talk about the matrix model. So recently, people talk about this C=1 matrix model and consider this non-singular sector, and they found many new interesting results, but there are more non-singular sector. They consider very specific non-singular sector, but there could be more like a larger sector in the matrix model. Is there some more like a future work or future direction for those sectors? Is there some? Yeah, this is somewhat naive question, but I just wonder whether there is interesting direction in that sector.
Can you repeat what sectors do you mean? I didn't catch it. Maybe.
Yeah, so in the long time ago, people consider just single sector of the matrix, SQL matrix model. And then Maldacena and those people consider non-singular sector. And then recently she and find the relation to the string and they calculate the instant correction and so on. But from the point of view of the matrix model, there are more non-singular sector. Even like in the past, like Kazakov, Kutasov, like three, yeah, Russian people also talk about some full sector of the matrix model, and they claim some black hole. Anyway, I don't understand that one, but I just wonder if there are some more future direction, some promising way direction in that, some more matrix model and other sectors better than.
I think the question is very similar to the determinant operators actually that we discussed before. So the determinant operators are also not strictly like singlet sector, like not single trace operators or any like multiple trace operators, but really like order n conformal weight operators. So yeah, I mean, basically you're asking whether there's some kind of dual D-brane or perhaps black hole description of those.
Yeah, so is there some other non-trivial background that string theory is due to those some non-singular sector? Yeah, And I just wonder, like, I also have some question about the chaos. People talk about the chaos in the like many, like n equal 1 over n correction and so on. But that means the spectrum is a chaos. But does it mean that that system, like n equal 4 Yang case, for example, people talk about the integrability and the 1 over n correction is a chaos. Does it mean that the n equal 4 Yang theory is chaos or not? Like when you say chaos, first of all, what does it mean by chaos? Is it just random matrix or like some OTOC or some other definition of the chaos? And the second one is that when you say chaos, what is exactly that means? Is it like a system is really chaos or some other quantity is chaos? Or so I wanna more need more. I would like to hear more some details.
Maybe I can take a stab at this and then people can correct me. I think that there is an operative definition of chaos, which might not satisfy a mathematician, but I think it's sort of good enough for many of us, which is to look at the distribution, for instance, of eigenvalues of some Hamiltonian. And there are statements that, depending on how the distribution looks like, you would call a system chaotic or not. And this has to do, I mean, this traces back to the classical intuition about chaos. So you have some classical system, it could be integrable or chaotic, and you try to promote it to a quantum system and you see which kind of spectrum you get. And the other thing is that you would certainly not call chaotic, I think, a system that has infinitely many conserved quantities that all commute among themselves. I think that's probably a fair statement. So an integrable system, I think, is very hard to imagine how it could be chaotic. Again, building on the classical intuition of what the motion could be for such a classical system. And my understanding is that while we have this integrable structure in some sectors or in some observables of n equal 4 superior means. If we took n equal 4 superior means at any finite value of n, then this would not be the case. Then you would not be able to find these observables. And maybe if n were like very, very large with respect to the type of observables that you're looking at, like Tristan was suggesting, maybe this violation is sort of small. And you can see that maybe you can have some control, but I think yeah, at fixed n, I think it just you don't have these symmetries. Maybe you could hope to have them in some approximate way. So then now people can correct me if this was my impression from our previous discussion, but people can please comment on it.
Yeah, I agree. Yeah, finite n equals 4 is like any other gauge theory. At large n, it exhibits integrability as an expansion. But that's it.
Yeah, like at finite n, you cannot have a set of infinite charges because traces of, let's say, an operator to the n, at some point they start depending on each other. So there is only a finite number you can have. So you cannot have infinite number of conserved charges if n is finite. And yeah. But perhaps the question of Tristan about the crossover, if there is such a thing as a crossover, once you have a definition of chaos, that may be an interesting question. And I don't know how to address this question for n equals 4. But perhaps you could start increasing n, and at some point, if you have a given definition of chaos, you could see whether there is a crossover. I am not entirely sure what we would see for n equals 4. If we would see a crossover, or for any finite n, we will have chaos and it's just in a 1 over n expansion where it's integrable. I don't know.
Maybe I can add just like a small thing. So yeah, like Alessandro said, in many body physics, there is a reasonably standard definition, this BGS conjecture that a quantum many body system, its spectrum is described by random matrix theory for some particular ensemble. And in n equals 4, at least for the perturbative spectrum, we were able to show that that was true. And so that would give you one way you could look at, is the distribution of level spacings and other observables like spectral form factor and so on, are they described by matrix random matrix theory? And then as you change n, do they cross over? And I do think you will find some behavior. I don't know exactly what it is yet. Of course, all these things are numerical. That's when I should say these are all numerical experiments. I don't have analytical results, but you should be able to see some sort of behavior, and that might tell you something about the case. And then I will also say there is a little bit more structure, exactly which ensemble the theory is described by, whether it's orthogonal or unitary or so on. Usually this depends on what other sort of symmetries are in the model. So yeah, OTOCs is one that, at least in this spin chain description, we haven't looked at actually. And there I wasn't quite clear what the definition would be, but the observables we looked at were the distribution of eigenvalues, the spectral form factor, which is related to correlation functions in the spectrum. And then the other thing is the eigenvectors. You can look at the entropy of it. So if you pick some particular state, some long, complicated gauge theory operator corresponds to some eigenvector of your dilatation operator, and you can ask, what is the entropy, what is the information entropy in that state with respect to some canonical basis? And that's another observable that you can look at, and also corresponds to random matrix theory in finite n. Sorry, I should also say, of course, Anna is going to talk about these things. She's not online at the moment, but she is going to talk about these things. Sorry, when is she going to talk about these things, Alessandro? I don't know.
I don't know. I mean, I don't
Anyway.
have the website in front of me, and also it's very
Yeah,
hard
okay, so
to give a
so
time
exactly.
given the different time zones, but it's certainly on the website. So
If you're interested, you should find the time. Anna Spearing is going to talk, and she will give more detail.
yeah. So I was wondering, Emil, do you have a comment or something to ask maybe concerning the discussion?
Oh, well, no. Still waking up a bit. So I've only caught the last 10 minutes or so of the discussion. I can actually, well, I can say maybe one thing about the question about matrix models. So yeah, the interest in non-singlet sectors, I think originally was the hope that by including them, you would get some kind of black hole physics. Because in other systems, like n equals 4 Young Mills, we know that's where black hole entropy arises, is by considering the n squared degrees of freedom of the non-singlet sectors. And in the C equals 1 matrix model as it stands, the inclusion of non-singlets, the non-singlets decouple when you take the scaling limit that leads to the so-called double scaling limit that leads to the continuum theory of world sheets. The non-singlet sectors have some energies which don't scale properly, so they leave the spectrum. So you can try to force them in by hand, but that means that you're basically changing the theory. So for instance, in the Euclidean theory, there's a paper by Kazakov, Kostov, and Kutuzov, where they said, okay, let's put in the operator that forces us to have non-singlets. It's some kind of vortex operator on the world sheet. And okay, you can do that. Basically, it means that the wall that keeps you out of strong coupling, instead of being a Liouville wall, is like a sine Liouville wall. Okay, you can do that, but it corresponds to changing the theory. So you're not forming something dynamically. You're just basically changing the background in which the theory is operating. And so that's number one. Also, the things that Xiyin is doing also correspond to sort of like forcing non-singlets into the theory, sort of one by one, by playing with the D-brane spectrum, sort of forcing D-branes in by hand. So I think my point is that you're sort of doing violence to the theory. It's not like you send in some wave packets, they form a black hole and decays dynamically. You're sort of changing the UV structure of the theory in a way that forces non-singlets in. And so all this, I think, is indications that this is not describing some black hole spectrum. This is describing just, changing the theory in some way. I think that's what I have to say about that. I did want to ask a question about, what you guys are talking about in terms of integrability versus chaos. So, I mean, are there hints when you consider, so how to say this? Again, the black hole spectrum is off at some energy that's of order n squared. And so the limit you guys are working in, you're sort of saying, well, I'm taking essentially n to infinity, so I can get this infinite set of conservation laws. And so you would expect sort of all this chaos structure, again, to sort of decouple. So are there any hints, though, at what sorts of, when you go away from the strictly infinite n limit and you consider operators whose size is of order, n or n squared or whatever you need to do to get to reach black hole structures, is there some qualitative thing you can see where some hint of something qualitatively different that you can still analyze, quantitatively, that indicates that the black hole spectrum is, lurking up there.
But is it clear that the chaos effect will decouple? Because also the size of the Hilbert space grows. So from what Tristan said, was a relation between n and the size of the Hilbert space. But if the size of the operator is like of order n, then also the Hilbert space grows, and perhaps one always has chaos for these systems. Maybe Tristan can say better, but.
But is there something sort of control that you can do?
Well, there's very little we can compute if the operators are of order n square. If the operators are of order n, there is some progress by people like Shota Komatsu and others. But order n square is just very hard. The operators are too complicated. The combinatorics is too complicated. It's just very hard. So yeah, so integrability helps you in the regime where, as I was saying in the beginning, where you can draw strings. So if you have a picture where the quantity you are computed is given by a string you can draw, it can be a complicated string, maybe a 4-point function with some interaction with the D-brane and so on. But if you can draw a string picture for it, you could expect integrability to help you and to have non-chaos. As soon as you have something more like a black hole and so on, which you cannot draw just with a string, you would expect chaos to kick in. But it's very hard to do a gauge theory computation saying this is absorption by a black hole, and I change a little bit the state and I see chaos, because those states are very hard to describe and the combinatorics are very complicated.
Yeah, and the same with Bootstrap. It could be great because you could explore gravitational physics, but the same problem arises. Like if the size of the operators is too big, then you cannot. It's hard to make progress.
Maybe can I ask a question? One different approach that we did not discuss at all during this discussion is the matrix bootstrap that Henry Lin and others have been trying to push about exploring the bootstrap for matrix models and also for loop equations and so on. And there they are trying to solve directly the matrix model at infinite n and to understand how the bootstrap could help you solve this 1 and 2 matrix models and so on. And I see that Robert DeMello is also in the audience. He also had some nice papers recently about it. And oh, maybe not anymore. He just left. Okay, so no.
He was in the audience indeed, but I don't.
He was. He had some recent paper about these master fields and so on in this language. So a question would be if in that language, if there are quantities where you study bigger operators. So right now, the bootstrap that was done was starting with correlators of single trace operators in these matrix models, order 1 operators, and imposing some positivity of some moment matrix. And you could ask, can I add to that moment matrix some determinant operators or even bigger and still study them in the large n limit and still learn something from that bootstrap? It's a simpler problem. It's not n equals 4, it's not gravity, but it's still one where even in the standard matrix models, right, correlators of big operators is going to be very hard. So I wonder if there could be something done there with the loop equations plus some bigger operators that we could see some qualitative difference between the kind of things we find for small operators, small words, and these big determinant operators. That could be a toy model for your question, Emil.
earphone.
I think is somebody trying to speak from Korea or?
Can I make one comment?
We hear you very faintly, I think. Hello?
Hello?
Yeah, that's better.
Oh, yeah, okay. There is one paper by Robert, the Mello coach. He's exactly studied some operator scale as square, which is due to LLM geometry. Then found some scrambling, fast scrambling from that spectrum. It might be some signature for the chaos related to very heavy operator similar with the black hole. Yeah.
Yeah, it's a pity that Robert is not here, but indeed, I think our time is winding up a little bit. So what I would suggest is that maybe we take just the last 5 minutes or so. If the panelists want to give some final thoughts, for instance, on the discussion, some final comments, and then we wrap it up. So Pedro, you want to start?
Okay, so I can just summarize what I just said in my presentation. So from integrability, we expect that any 1/n correction we can draw as a string, we should be able to eventually compute. Whether we can compute it efficiently or not is tied to the question of whether we can get rid of all these sums over intermediate states. It's not crazy to think that we can, because sometimes it was done, but it's also not crazy to think that we cannot, because some correlators in some integrable theories are just given by infinite sums, and that's the end of the story. So if you ask, say, 4-point function of 4 stress tensors in sine-Gordon theory, it will be given by a bunch of infinite sums, and no one thinks I should be able to do better than this. It's the end of the day. So if you go beyond quantities that you can draw as a string, you should not expect integrability to help you, but maybe other tools can help you.
Lorenz?
All right, yeah, I can also more or less repeat what I said in the beginning. So perturbative string theory, what I was talking about is like more or less like in the techniques, I think not so much has happened in the last years, but we see that it's been applied to many new situations now and with success. So I hope that will continue. And I also think that now we're getting new techniques from outside that were not there like 10 years ago, like the bootstrap, like what Fernando was talking about, and the hexagon that Pedro was talking about. Maybe. And yeah, so I think we should also really try as a community to again tackle like perturbative string theory. I feel like people have left it a little bit on the side and like are talking about new exciting things, but it's still like the only like fundamental description we do have of string theory. So it's the backbone, and we should really try to like make progress on it and try to compute like these higher genus amplitudes, because there's no fundamental obstacle of throwing this on a computer. It might be complicated, but still, like we should be able to throw it in a computer and spit out some numbers and compare with other approaches. And I think that's something we as a community should do. All right, so that's my plea. What should happen? Thanks.
Thanks. And finally, Fernando.
Yeah, I think like what it would be nice that, and I think it will happen, is that now different techniques will start coming up together. So we have a lot of techniques that work very nicely in a 1/n expansion, integrability, also this analytic bootstrap. But on the other hand, things like S-duality and the numeric bootstrap are also okay, are friendly for finite n. And I think as we combine all these things together, I think we may start getting like a better and better picture of at least systems where we have ADS. Yeah, and I think that's what is going to happen, and is already happening somehow, that these techniques, they come together. And I don't think we will understand fully the problem by any given technique. We will have to combine all these things. Yeah, and I think that's the punchline, I think.
Great, great. Yeah, yeah, it's a great punchline, and also a great sentiment. And I think some of the, I enjoyed the discussion very much. Some ideas came out, and I really hope that we will see a lot of progress in this field and like across the different type of ideas that were put forward. So I thank you very much to the panelists for participating. I thank you thank again the audience for taking part in the discussion. And I think that with this, I would give the floor back to Korea, where it's probably time to go to sleep. Thanks.
Thank you so much.
Thank you. Thanks a lot.
Thank you.
Thank you very much. Yeah. Yeah. See you. Yeah. It was very nice. Yeah. I'm very
As a comment, Robert is back. If we do want to hear from him, we would have a chance.
It's yeah, maybe it's a bit extra time now, but yeah, what would be nice, I think, is that maybe on the website, if people, that's a suggestion to the organizers, we do it in Florence at GGI. People can send to the organizers additional comments on the discussion. They can maybe published on the website as sort of supplemental, you know, some Q&A or things like this, even if they come up a bit later when people that could not, you know, watch the thing live want to send the questions, that could be an idea. So if people can send the questions to the organizers or comment, they could either refer it to the panelists or just publish it, and we can have some supplemental discussion on the website if that's all right with the organizer. That's just a proposal, but
okay. Then I
people that
will
couldn't
find some
attend.
way to do that. Yeah, I will discuss with the others and find some nice platform to have some online discussion. Okay. Yeah, thank you very much for today.
Thank you.
It was very nice. Yeah, thank you.
Bye. Bye.
Yeah, bye. Have a good day. Bye.